Hey guys, so today we're going to be doing a Gauss law question for an infinite sheet of charge. So our goal using Gauss law is to find the electric field of this infinite sheet. Now Gauss law is given here. It shows that the flux is equal to the integral of E dot dA. So essentially the only two things we need to do is to compare this with the other equation for flux, which is the enclosed charge over the permittivity of free space. So when we equate these two, we will be able to find the value of the electric field, which is then going to give us a lot of intuition about how this system works. So the three things we need to find here are E, dA, and the charge enclosed. So we're going to start by drawing a Gaussian surface. I'm going to choose just a little cylinder because it doesn't really matter in this situation because the sheet is infinite. So first I'm going to look at the charge enclosed. Now I know that the surface charge density is sigma, and I've defined my area to be just A. So inside this flat surface of the disk, the charge enclosed just is the density times the actual area. So we have sigma A. Now the next thing to do would be to find what E dot dA is. Now when we look at this sheet, we notice that the field is going to come from two directions. It's going to come outwards on our side of the field, and it's going to go inwards on the other side of the field. So if the page is the field, there's going to be a set of electric field coming outwards from us, and there's also going to be some going into the page. So the goal would be to find the element of E dot dA going outwards, and also the element of E dot dA going inwards. And when we equate these two, we're going to be able to find the total E dot dA. So let's consider the outwards first. The E field is going in this direction, so let's just label an arbitrary axes. Let's call this X, Y, and Z. The E field is going in the Y direction, and dA is also pointing in that same direction. So we would say that the E dot dA in this situation is equal to E y hat dot dA y hat, and y hat dot y hat is just equal to 1 because they're unit vectors and they're in the same direction. So this element is equal to just E dA. That's the first part. Now doing the same thing the other way, we want to find the E field going into the page, going outwards. And we do this using the same method as before. So we have our set of coordinate axes, and we're going into the page. So E is in the negative direction, and our area vector is also in that same direction. So for the second term, we have E in the minus y hat direction, dot dA, which is also in the minus y hat direction. So the minuses cancel out on each other, and we get the same thing as before, which is E dA. Now adding these two terms together, we get the total E dot dA, which is simply 2 times E dA. So we finally found all the terms we need to do our Gaussian integral. So we're going to start off by just doing it. So the integral E dot dA is equal to just 2 times E dA, and that is equal to the total charge enclosed, which is the surface charge density times A divided by epsilon naught. Now, technically, it would be possible to break these down into circular coordinates, polar coordinates, and to get the area of the circle when we integrate. But when we're going to see that this has an A on the right side, so if we technically just don't worry about that, we're going to notice that the A's are going to cancel out eventually. So the integral of this is the same as 2E times A, which is equal to sigma times A over epsilon naught. So now we're going to cancel out the A's as we saw before, and we're going to end up with our final value for our E field. Now, notice that this only works if we assume that the sheet itself goes to infinity, because then that way we can take an area however large we want it to be, and this would still be the case. If this sheet wasn't going to infinity, then we'd have a specific case for near the surface. Then as A would get large, we'd have to introduce another case, and then we'd have to just show that the E field is 0 when there was no charge enclosed on the outside. But that's a different problem. For this problem, the E field is sigma over 2 epsilon naught.